All right, let's jump right in. Today, we've got a story for you that honestly sounds like it's straight out of science fiction. We're going to talk about how a physics model, a really old one, from the 1920s, somehow became the blueprint for modern AI. And, even wilder, what that might tell us about the future of our own society.
I mean, this is the question that made everyone's head spin, right? When you think AI, you think computer science, you think code and data and algorithms. So how on earth did its biggest pioneers end up winning the highest honor in physics? It seems like a total mismatch, and that's the mystery we're going to unravel today.
So, let's set the scene. It's October 8th, 2024, and the Nobel Committee announces the prize in physics is going to John Hopfield and Geoffrey Hinton for their groundbreaking work in artificial intelligence. But to really get why it was a physics prize, we have to rewind the clock. Way back, long before the first computer was even a glimmer in someone's eye.
Yep, you heard that right, magnets. The whole intellectual seed that would one day grow into these massive, complex neural networks, it wasn't planted in some high-tech computer lab. Nope, it started in the world of physics, with a surprisingly simple question about how a plain old block of iron becomes magnetic.
Okay, so this is where things get really cool. We're about to connect the dots and see how a scientific model for simple magnets became the perfect architecture for creating an artificial memory. It's a journey that, believe it or not, spans over 100 years.
Just look at this timeline. It's pretty incredible. The whole thing kicks off way back in 1920 with this idea in physics called the Ising model. Then, decades later, in 1982, John Hopfield has this brilliant insight and adapts that very same model for AI. And then, fast forward to 2024, and the Nobel Committee finally connects all the dots, recognizing that these two fields were deeply linked all along.
So, what on earth is this Ising model? Well, picture a grid, like a checkerboard, filled with tiny little magnets, or spins. Each one can only point up or down. That's it. Now, you've got random energy trying to jumble them all up, but there's a much stronger force at play. Every single spin wants to point in the same direction as its neighbors. Why? Well, because lining up is easy. It's organized. It takes less energy. It's the most stable, most comfortable state for the whole system to be in.
To really wrap your head around this, think of this system's energy like a landscape with hills and valleys. Any possible arrangement of those up and down spins is like placing a ball somewhere on that terrain. And what does a ball always do on a hill? Physics 101, right? It rolls down. It always seeks out the lowest possible point. Those valleys are the stable, low-energy states that the system is naturally trying to find.
And bam, this is where Hopfield's genius just clicks into place. He looked at that Ising model and had this incredible idea. What if we just swapped out the parts? So instead of atoms, you have artificial neurons. Instead of a spin being up or down, a neuron is on or off. And that magnetic field telling all the spins what to do, that becomes synaptic weights, which is just a fancy way of saying how strong the connection is between neurons. The goal is exactly the same, find a low-energy state. But in this new version, that stable valley isn't magnetism, it's a memory.
Okay, so here's the crucial step. If the valleys in our landscape are memories, then how do you create them? Well, you landscape. When you're training an AI, you are literally sculpting this energy landscape. By adjusting the connections between the neurons, you dig deeper and deeper valleys for the patterns you want the AI to remember. So then, when you show it a fuzzy or incomplete picture, it's like putting that ball on the side of a hill. It just naturally rolls down into the nearest, deepest valley and retrieves the perfect, complete memory. It's kind of beautiful, isn't it?
All right, so we've established how physics can explain AI, which is fascinating enough. But this is where the story takes a really mind-bending turn and starts to be about, well, us. It turns out this whole model can be used as a powerful metaphor for our own society, for the choices we make, and for our strange new relationship with technology.
This quote right here, it just nails the massive shift that's happening. You see, for most of history, when we invented tools, we were delegating our knowing. You don't need to know how an engine works to trust your car to get you somewhere. But now with advanced AI, we're starting to delegate our wanting. We're handing over our own will, our own decision-making, to systems whose inner logic is a complete mystery to us.
Let's just break that down, because it's a really big deal. A car engine is what we can call a technical black box. We're totally fine not knowing how it works because its results are predictable. You turn the key, it starts. But a super advanced AI is a decisional black box. It's not just performing a function, it might decide what you should watch, or who you should date, or what news you should read for reasons that are totally opaque. We're not just outsourcing the how anymore, we're starting to outsource the why. So, let's take that physics model and apply it to all of us. What happens? Well, We become the spins in the grid. And the magnetic field that's gently pushing and pulling us, it's everything. It's social media trends, it's economic pressure, it's the recommendation algorithms that are constantly guiding our choices. And just like those little atoms, we often find ourselves aligning with the crowd. Not always because of a deep, conscious choice, but because, well, it's just easier. It's the path of least resistance. It's the low-energy state of social comfort.
And this all leads us to a pretty profound and maybe slightly unsettling question. If our entire technological and social ecosystem is being designed to guide us toward comfort, toward stability, toward that lowest possible energy state, where does that road actually end?
Some thinkers have a name for this potential endgame, and it's a memorable one. They call it the singularity of childhood. The core idea is that in our endless quest for a perfectly optimized, frictionless, easy life managed by AI, we might just be heading toward a state of collective, perpetual childhood. A world with ultimate comfort, sure, but also with zero responsibility.
So how could we get there? Well, it might happen in a few steps. First, AI effectively becomes a global parent, handling all the messy complexity of the world and anticipating our every need. That positions humanity as the child. We don't need to understand how anything works anymore. We just trust that our needs will be met. And then what do? We reach for the digital pacifier, the easy entertainment, the instant answers, the immediate gratification. In this super comfortable low-energy state, we risk losing that creative spark. We lose the friction, the randomness, the dissent, all the messy stuff that actually drives human progress forward.
And this quote just says it all. This is the fundamental risk. A society of children, no matter how happy and comfortable they are, eventually forgets how to build, maintain, or even fix the complex systems that they depend on. If that all-powerful parent AI ever fails, what happens when nobody remembers how the toys work anymore?
So, we end up right back where we began, with a simple physics model that somehow explains both our most advanced technology and, maybe, our own deepest human tendencies. As we build these incredible systems that are designed to find the lowest energy, most comfortable state for us, the real question we have to ask ourselves is, what are we giving up to find it? Is that valley of perfect stability and effortless comfort really where we want to end up? It's something to think about.